All right, let's dive right in. Today, in this explainer, we're tackling one of the biggest, most fundamental questions there is. Where did life come from? We're going to explore a really compelling new answer to that very question.
Just try to wrap your head around this for a second. Picture early Earth. It's this chaotic, bubbling soup of simple molecules, water, and it's getting zapped with energy. So how do you get from that to something that's alive? Where do you even draw the line between just a bunch of chemical reactions and an actual living thing?
You know, scientists actually have a name for that line. They call it the autonomy threshold. It's that invisible barrier that a system has to cross to go from being just a passive collection of stuff to being an active, autonomous individual that can act for itself. So the real question is, how do you cross it?
Well, this is where a fascinating new theory called CREAT comes in. CREAT stands for Constraint-Resonance Emergence Theory. And what it does, really, is provide a kind of recipe, a step-by-step guide for how a system could literally pull itself up by its own bootstraps and make that incredible leap into life.
So how does CREAT do it? Well, it breaks this massive, overwhelming problem down into 3 different layers, 3 levels of organization that are all interacting with each other on totally different timescales.
Okay, the easiest way to think about this is to imagine building a factory that can build itself. Down at the bottom, on the fastest, tiniest scale, you've got the microdynamics. These are your raw materials, your nuts and bolts, just individual chemical reactions. Then in the middle, you have the mesostructure. These are the machines on the factory floor. And the cool part is, they're self-building machines called autocatalytic networks. And then at the very top, you've got the macro constraints. These are the factory walls, the building itself, a compartment that holds the whole operation together.
All right, so let's start at the ground floor and build our way up. How do you go from just a random soup of chemicals to a working, self-building engine? The great thing is, early Earth was basically the perfect startup incubator. You had all the ingredients you needed, a huge diversity of chemical building blocks, these monomers, just floating around. You had tons of energy being pumped in from sunlight and geothermal heat. And, this is key, the whole system was far from equilibrium. It wasn't just a boring, stagnant puddle. It was a dynamic, churning environment just waiting for something amazing to happen. And this brings us to this critical insight from a scientist named Stuart Kauffman. What he realized is that in a chemical soup that's rich enough, you don't need some miracle to get things organized. You just need one thing to happen. On average, each molecule needs to help create more than one other type of molecule. As soon as you cross that simple line, the math says it's basically inevitable that the whole system will just snap together into a giant, self-reinforcing network. And it all comes down to this one magic number, 1. The moment the average number of reactions a molecule catalyzes ticks over from, say, 0.99 to 1.0 or more, the whole system flips a switch. It's a phase transition. It goes from a collection of random, disconnected reactions to a coordinated chemical engine. That's the first huge leap upward.
But here's the problem. Having this awesome new chemical engine is great, but if it's just running out in the open, it's not going to last. That brand new autocatalytic set needs a home. And that brings us to the next crucial layer.
I mean, think about it. Without some kind of container, all those molecules that are part of our new engine would just drift away from each other. The reactions would slow down, and the whole beautiful structure would just dissolve back into the soup it came from. It has to be contained.
And that's where the walls of our factory come in, the macro constraints. These could be things that form naturally, like little bubbles of fatty acids called vesicles that trap the chemistry inside. But here's where it gets really interesting. The boundary does more than just hold things in. It starts to influence what happens inside. And this is a game changer, because for the first time, information is flowing down. The home starts shaping the chemistry it contains, maybe by favoring reactions that help make the walls stronger or more stable.
Okay, so we've got this upward pressure from the chemistry organizing itself into an engine, and we have this downward pressure from the container shaping that engine. When these two forces meet and start working together, well, that's when life can finally get started.
This is the core of it all, this beautiful feedback loop. Let's walk through it. Step 1, you've got your molecules. Step 2, they spontaneously form that self-catalyzing set, our engine. Step 3, that engine starts producing things that build and maintain its own compartment. The factory starts building its own walls. And then, this is the genius part, Step 4, the compartment, the walls, then helps to stabilize and select for the very chemistry that built it in the first place. The loop is closed. It's a completely self-sustaining, self-constructing system.
And Creed gives us a way to put a hard number on this moment. It's called the loop gain. If the gain of that feedback loop is less than 1, the system just can't keep up. It loses stuff faster than it can make it, and eventually, poof, it dies out. It's just a collection of reactions. But the moment that that loop gain hits 1 or goes above it, bam, the system becomes self-sustaining. It crosses the autonomy threshold. It's no longer just chemistry. It's an autonomous individual. It's a protocell. It's alive.
Now, I know what you might be thinking. This is a really neat story, but is it actually science? And the answer is yes. And that's what's so powerful about Crete. It's not just a philosophical idea. It makes concrete, testable predictions that we can actually check out in a lab right now.
For instance, take this idea of cheap disruption. The theory predicts that it should be way easier, it should take much less energy, to destroy the whole system by just popping its container, than by trying to go in and destroy every single little catalytic molecule inside. And if you think about it, that's exactly how a living cell works, right? It's pretty easy to pop a cell membrane, but it would take a ton of work to chemically dismantle all of its internal parts one by one. So what's the big takeaway from all this? Screet doesn't just give us a plausible recipe for how life got started. It actually offers us a whole new way of defining what life is.
This one sentence from the paper just nails it. It really captures the whole idea. Life isn't about one special molecule, like DNA. It's about a process. It's that specific moment when a chemical system figures out how to build its own house, and in doing so, locks itself into a state where its own existence becomes self-fueling.
And that right there is the crucial distinction. Below that tipping point, that gain of 1, you just have a bag of interesting chemistry. But the second it crosses that line, you can stop talking about individual molecules and start talking about the system as a whole. You can talk about its health, its purpose, its life. It has become an autonomous system.
And this leaves us with this wild final thought. If life is fundamentally defined by this kind of self-constructing, self-maintaining feedback loop, what else out there might qualify? Could the same pattern of organization show up in totally different places? Could we find a form of life in the complex information patterns of a computer, or the plasma dynamics inside a star, or maybe even in the self-sustaining structures of our own economies? The recipe might just be universal. Thanks for joining The Explainer.